Hello, welcome to this function review. Basically a brief overview of functions and their notation and how to use them. So I have an example here of a function that says f of x equals 5x squared plus 3x minus 2. That has a function name of f. That helps us determine what function we're talking about if we're using more than one at a time. X is the input value here, and f of x collectively, the function and the input, represents the output, which is calculated from the actual equation on the right-hand side. So if we want to plug in a value, such as 4 here, we'd plug it in everywhere we have an x, and then we would get 90 out. So basically, x is 4, and the output, which is usually called y in some cases, if not f of x, is 90. So the notation here, f of 4 equals 90, is used to show not only what function we were working with, but the input-output values together. So, calculating function values. I said that naming a function is pretty important to help you understand which function you're talking about. And here I've got two functions. F of x equals 4x plus 2, and g of x equals negative 3x plus 5. So when I'm asked a question here that says find f of 2, I know to look at the f function and plug 2 in. So 4 times 2 plus 2 is 10. This means there's an input of 2, an output of 10. Graphically, you could think about this as x is 2, y is 10, and that would be a point on the f graph. The second example, g of 6, tells me I'm looking at the g function. So I'm going to plug 6 in everywhere I have x. Negative 3 times 6 plus 5 would give me negative 13. So the input is 6, the output is negative 13, written as g of 6 equals negative 13. You could look at this as x is 6, y is negative 13, and that would be a point on the g graph. Next thing I want to talk about is domain and range. So if you want to talk about domain is all the x values that a graph covers or a function covers. Graphically, this is not too hard. So if we want to just talk about x, which runs from left to right, we can look at the graph here, the first one I have, and we look at the x-axis and we see the smallest number used is negative 3 and the largest is 1. So that domain is from negative 3 to positive 1. The second graph does not have any endpoints. It just keeps opening wider and wider. We could say that domain is all real numbers, or it runs from negative infinity to positive infinity. Okay. Range is the y values or the outputs of a function. So when we look at a graph, these are the axis that runs up and down. So in the first graph, the smallest value used on the y-axis is 0, and it runs up to 2. So that range is 0 to 2. And on the second graph, it starts at negative 2 for y and continues to go up. So negative 2 to infinity. So as far as if we were working with just straight equations and didn't see a graph, we usually start off saying the domain of a function is all real numbers, unless otherwise stated. If there's something given in the problem that tells us that we can't use negatives or that we can't produce more than 60 items, then that would limit our domain. Or, in some cases, just the way an equation or a function is written, it's mathematically implied what the domain might be. So we're going to look at two concerns. The first is dividing by 0. So if we want to talk about the domain of a function, we know that we can't divide by 0 because division by 0 is undefined. So if we see a fraction and it has a variable in the denominator, we need to inspect this. So if a variable is in the denominator of a function, you must restrict the domain to prevent dividing by 0. You don't want the bottom to be 0. So you do this by setting the denominator not equal to 0 and solving for the variable. So you only have to look at the denominator in this case. So here's an example. F of x equals the fraction where the numerator is 5x minus 3 and the denominator is x plus 2. So we have a variable in the denominator. We only have to look at that denominator. So we set the domain equation up to be x plus 2 does not equal 0. Isolate x, so x does not equal 2. So this means this function would take all real numbers and give us a value back except for negative 2. If we plug in -2, we get 0 on the bottom, which means it would be undefined. Okay, I have the graph of this function off to the right. We haven't talked about graphing this, and it's zoomed out really far just so you can see how extreme it is, but there is a break there around what you would have to guess being about -2, but you can see there's a break in the graph where there's no value. Next, the other domain concern that we're looking at right now is imaginary numbers. You may know that if you try and take the square root of a negative number, it does not give you a real value. It goes into the imaginary complex system. So we want to stay away from that because it's not very useful in business. Doesn't really work out well for graphs. So you must restrict the domain so a negative does not end up under the root. So to do this, you create an inequality such that what is under the root is greater than or equal to 0. That means we're going to keep what's under the root non-negative. So the smallest it could be is 0. So let's look at an example. F of x equals square root of 5x plus 7. So what's under the square root is 5x plus 7. We don't want that to be negative, so we'll set up the inequality 5x plus 7 greater than or equal to 0. We'll isolate x and solve this inequality. We get x is greater than or equal to -7/5. Okay. This means that the function will give a real output if the input is -7/5 or greater. So as long as we pick something bigger than -7/5, this square root function will give us a value back that makes sense. If we pick something less than -7/5, it will go into a negative root, and that will give us something that does not make sense for our applications. And I have the graph of the square root function over to the right here. And once again, graphically, you might not be able to pin this down to exactly -7/5, but you can see it's right there where it should be. So there's no graph to the left of -7/5 on the x-axis, and all the graph is to the right. Thank you.